So in this video, we're going to talk about torque and how torque is a product of force and the moment arm. We'll use the biceps curl as an example of how a muscle generates torque in response to an externally applied load, such as a dumbbell, and briefly describe the center of gravity of the body and how that's a function of the torques produced by the individual segments of the body. So let's say we have a force here that's applied in line with an object's center of gravity. We know, according to Newton's laws of motion, that that force will produce what's called linear motion. However, if that same force is applied off-centered or not in line with the center of gravity, that force is known as what's called eccentric force, not to be confused with the eccentric contraction of a muscle, which is when the muscle contracts while it's lengthening. The eccentric force in this context simply means the force is applied off-centered, not in line with the center of gravity. So as a result, it would tend to produce angular motion, which is basically motion around a fixed point, or around a pivot or axis of rotation. We call that tendency of a force to rotate an object torque. You've heard the term before. Some other terms that have been used to describe the same thing is moment of force or moment. In fact, I use joint torque and joint moment interchangeably. They pretty much mean the same thing. So it's the tendency of a force to rotate an object about what's called the axis of rotation. And it's dependent on two factors. It's dependent on the magnitude of the force itself, as well as the distance between that axis of rotation and the line of action of that force, and more specifically the perpendicular distance or the perpendicular component of the lever arm. This is known as a moment arm. Very important to distinguish the difference between a moment arm and a lever arm. Lever arm is simply the distance between the axis of rotation and the force of application. So if you know your anatomy, just think of the distance between the axis of rotation of a joint, say the elbow joint, and the insertion point of the muscle. The moment arm depends on the angle of rotation of that object, of that joint. And it's the component that can actually rotate that specific joint. So let's take elbow, for example, and we're looking at the biceps force here. So that is the force produced by the biceps muscle. The lever arm, or the radius, and in fact I'll label it as R, is the distance between the axis of rotation, in this case the elbow joint, and the insertion point, or the force, or the application of the force of the biceps. Now the component that would rotate the elbow, in this case inflection, is known as the moment arm, which is calculated off the sine, or you guys know sine is opposite over hypotenuse, and so sine theta, or sine of the angle of flexion in this case, multiplied by R, or the lever arm, gives us the moment arm. And at 90 degrees, we know that sine 90 is 1, and so therefore the moment arm is actually equal to the lever arm at this angle. So it's very important. So the force that's produced by the biceps in this case would have its maximum torque at 90 degrees, simply because R in this case equals D, or the moment arm is equal to the lever arm. Okay, so let's take another physical example. Let's just say that someone's holding this dumbbell here, and they're doing a squat. So the weight that is produced by this barbell, or I'm sorry, this dumbbell, would produce its maximum torque about the shoulder joint, because look at the moment arm. Remember, moment arm is a perpendicular distance from the axis of rotation, in this case the shoulder, to the point of application. In this case, we're just looking at the weight of the dumbbell in this case. So in this case, it would produce a torque that would tend to extend the shoulder joint. Okay, so let's take a look at another example. Now we have the person has a shoulder flexion, let's say 120 degrees or 130 degrees. Look at the moment arm. The moment arm is now shortened. Or if I look at it this way, let's say that the person dropped the weight a little bit, and this now is at 45 degrees of shoulder flexion. Its moment arm is also shorter. In fact, if we were to compare the moment arms at this angle versus the moment arm at 90 degrees, look how much shorter it is. Think about it. If you were performing this exercise, would it be easier to hold that weight directly in front of you, or at 120 degrees of shoulder flexion, or 30 degrees? you would say either 120 or 30 because the weight is closer to you, more specifically closer to the axis of rotation. In this case, the moment arm is smaller, so therefore the torque that externally applied load produce is also smaller, right? It's a direct correlation. It's directly proportional, moment arm and torque. Torque is a vector quantity, just like force, so it has both magnitude and direction. The direction of torque is associated with the rotation that it caused, either clockwise or counterclockwise. And counterclockwise is typically, according to the right-hand rule, is typically considered to be positive, while clockwise is considered to be negative. The metric units for torque is a Newton meter. Just you got to remember that Newton is a unit of force and meter is a unit of displacement or length. So let's talk about direction here. Right hand rule. You got to use your right hand. With the four fingers, you rotate in the direction that the actual rotation occurs. So for example, counterclockwise is this way, and the direction of thumb indicates the direction of the torque. More specifically, the axis of rotation. Remember in my previous videos, I talk about axis rotation as the axis that's perpendicular to the plane defined by the other two axes in a three-dimensional sense. So if I'm looking at the axis of rotation, I follow those two axes that define those plane. We take what's called a cross product. You don't have to know this for this particular lecture. The direction of the thumb indicates the direction of the torque. So counterclockwise is positive. Clockwise, if I'm following in the other direction, is negative. So now let's talk about torque in the context of muscular contraction. As I mentioned earlier, torque is a product of the magnitude of the force as well as the location of the moment arm. Say for example, you've got the elbow joint here. The fulcrum, which is represented by F, is the axis of rotation of the elbow. The L here represents an externally applied load, which is the weight of the forearm. And an E here represents the effort force of the bicep muscles. So muscles generate angular motion through these torque, which, as I mentioned, is a function of the force generation of the muscle itself, as well as the location of the moment arm. So moment arms can have a significant effect on joint movement. We talk about joint positions which determine the moment arm, so we know there are certain positions that joints have that have the maximum generation of force and subsequently the maximum generation of torque in order to move that joint into flexion, extension, abduction, adduction, internal or external rotation. Let's take the knee joint for example here, and more specifically the quadriceps. If you know your anatomy, you know that the force is transmitted to through the patellar tendon and through the quadriceps tendon via the patella. The patella bone acts as an extension of the quadriceps moment arm. If you didn't have that patella, the moment arm would be significantly decreased, and therefore the quadriceps would not be able to rotate that knee joint into extension. But because that patella is there, and we know that there's a little bit of tracking in there, the quadriceps is able to produce a torque that would tend to extend the knee or tend to rotate the knee into extension, as many of you know. So whenever you get confused about torques, or muscular torques specifically, just think about your anatomy. You kind of already know what these muscles can do, or at least the actions. Quadriceps, knee extension. Hamstring, knee flexion. Now just do that in the context of torque. Quadriceps produce a knee extensor torque. Hamstrings produce a knee flexor torque. So just think about your anatomy and then you'll understand the torques that these muscles can produce. Why is this so important? I think I already answered that question, right? Muscles produce forces about an axis of rotation that would tend to either extend, flex, abduction, adduction, or internal external rotation, depending on the origin and insertion of that particular muscles. It uses a system of what's called levers. Lever is what I showed you earlier, is a system in which that torque is applied that includes the pivot point, more specifically the axis of rotation, the muscular force of the force generated by the muscles itself, and an externally applied load. And there are three different classes of a lever system, and if you take and apply kinesiology or applied anatomy, this will be a little bit of review for you. So a first class lever is one in which the fulcrum or pivot point is in between the effort produced by the muscle and the load, in this case, which is the weight of the head. E is the force of the sternocleidomastoid muscle here, and this is the axis of rotation at the head and neck joint there. So that we call is a first class lever. Second class lever is one in which the load, in this case the weight of the body, is in between the pivot point, the fulcrum, and the force of application of the muscle. And so in this case, this is the plantar flexors, the gastrocnemius and soleus muscle through the Achilles tendon would produce a load here and generate a force, a torque that would tend to plantar flex the ankle joint. So that is a second class lever. Third class lever is probably the more common lever systems in the body. The one that we're using in this lecture is the elbow flexors. And this is one in which the muscular effort, or the force due to muscular effort, is in between the fulcrum and the externally applied load here. So we're going to use the bicep curl as an example of how torque is produced, and calculating the force that the bicep produces in order to counter, say, the weight or the torque that's produced by the dumbbell. We'll call this bicep curls kinetics. So let's look at the example I showed you earlier. We're going to make what's called a free body diagram, which displays all the forces and moment arms that's associated with this particular system. The system in this case is the elbow joint, more specifically the upper arm and the forearm. As I mentioned earlier, the elbow axis of rotation is the fulcrum. E, it represents the biceps force, and L is the externally applied load, aka the weight of the forearm. Now we're going to add the dumbbell. So the person's holding a dumbbell that has a certain weight, and weight is in the direction of gravity, right? In this case, in the vertical direction, more specifically the negative vertical direction, like towards the center of the earth. And here going to represent F subscript F represents the weight of the forearm. F subscript D represents the weight of the dumbbell. Moment arm of the dumbbell is represented here. Remember, that's the perpendicular distance from the axis rotation to the line of action of the force, in this case the weight of the dumbbell, the weight of the forearm. And the moment arm of the muscle at this angle, 90 degrees, is represented by that blue line, which is the perpendicular distance between the axis rotation of the elbow and the insertion point of the biceps muscle. Okay, so we're going to use this free body diagram to calculate the force that is needed by the biceps in order to counter the torque produced by this dumbbell, as well as the forearm's weight. So we're going to look at this at the isometric contraction, the isometric hold. How much force does the bicep have to produce in order to hold that weight? And so according to Newton's first law, if there is no motion, it is at rest, that means the net force is equal to zero. Since we're talking about angular motion, the net torque is equal to zero. Remember, torque is a tendency of a force to produce angular motion. So Newton's first, second, third law also applies to angular motion. In this case, the sum of the torques must equal to zero if the person's just simply holding it. The isometric hold, right? All right, so let's put some numbers here. I've got here the same scenario. I'm drawing my free body diagram. The weight of the forearm is 10 newtons. The weight of the dumbbell is 100 newtons. And we know that because the weight is in a negative direction, it would tend to extend the elbow. Makes sense, right? If you didn't have any muscles there, your elbow would just drop into extension. The moment arm of the dumbbell is 50 centimeters. For the forearm, it's 40 centimeters. The moment arm of the elbow flexors is 4 centimeters, as displayed here. Using this free body diagram, we can use all of this information to calculate the force that is needed by the biceps muscle in order to balance that dumbbell in this scenario. So Newton's first law, as I mentioned earlier, you sum up all the torques and set that equal to zero. In this scenario, just do it one by one. Calculate the torques produced by the dumbbell as well as the forearm, as well as the biceps muscle itself, using E as a variable that we hope to solve, that we will solve. Okay, so the torque produced by the dumbbell here is its weight. Remember, it's negative because it's in the negative vertical direction, multiplied by its moment arm, which here is 50 centimeters, and that gives us negative 50 newton meters. For the forearm, it's negative 10 newtons multiplied by its moment arm, which is 40 centimeters, and you get negative 4 newton meters. The torque produced by the biceps muscle is E, which we were trying to solve, so that's just a variable, multiplied by its moment arm. So you set all of that equal to 0, and you solve for E. So in this case, negative 50 minus negative 4, put that on the other side, you get roughly 1,350 newtons. That is more than 10 times the weight of the externally applied load of the forearm as well as the dumbbell. So think about it. Why do you think the muscle has to produce a significant amount of force there? Because the moment arm is only 4 centimeters compared to the moment arm of the forearm and the dumbbell. So your muscles have to contract a significant amount of force in order to maintain that isometric hold. And in a separate video, I talk about muscle contraction and muscle mechanics and how your muscles are powerful in that regard in producing that force in order to counter these torques. Okay, so that's an example. Now I want you to try it. I've got the same exact scenario. The only difference is the weights are slightly changed as well as the moment arm. So we've got here the dumbbell, 125 newtons. The forearm is 12 newtons. The moment arms of the dumbbell and the forearm is 60 and 40 centimeters respectively. The moment arm of the bicep muscle in this case is 2.5 centimeters as displayed here. Use this free body diagram in order to calculate the force needed by the biceps muscle group to make this isometric hold while it is essentially holding that dumbbell. So go ahead and try it. Okay, so the way you solve this free body diagram is the same way you solve any math or physics problem. You identify what you know, so we know the weight of the dumbbell, the weight of the forearm, their respective moment arms, and the moment arm of the bicep muscles. And what we're trying to solve, which is the unknown, is this guy right here, E, which represents the force that the biceps need to exert in order to balance the torque created by the forearm and dumbbell. So what I would do is, because we know it's not moving, therefore, according to Newton's first law, the sum of the torque, or the net torques, is equal to 0. So solve the torques for each respective weight. Should be simple. So the torque created by the dumbbell is negative 125 newtons multiplied by its moment arm, which is 0.60 meters. The torque created by the forearm, that's the weight of the forearm, it weighs 12 newtons, or negative 12. Remember, it's negative because weight is in the negative vertical direction. That's the line of gravity, multiplied by its moment arm, 40 centimeters. And then the torque created by the biceps, we're trying to solve E, trying to figure out what that force is, multiplied by its moment arm, 2.5 centimeters. You set all of that equal to 0, and we want to solve for E. So if you do the math, this is what you end up getting. Let's see, should be, if we add these two up, that ends up being a positive 79.8 newton meters. Divide that by 0.025 meters, or that's 2.5 centimeters. Plug that into your calculator, you should get roughly 3,192 newtons. Voila. Okay, so now we're going to talk about the relationship between torque and center of gravity, more specifically center of mass. Every object has mass, and depending on its distribution and the amount of mass in that object will ultimately determine its center, its balancing point. So if we're talking about a ball or a sphere that has both uniform mass distribution, its center of mass is going to be right at the center. And if we're talking about it in the vertical direction, where we're looking at gravity and looking at weight, we're talking about the object center of gravity, which is the location of which all the torques will sum into zero. That means the torques due to the individual segment's weight, or the torques produced by the individual segment's weights. And in the context of the human body, because the human body is made up of multiple segments with different mass distributions, like the human torso has multiple cavities, the head is solid, the limbs, the upper limbs and the lower limbs tend to taper off, so the locations of its individual center of masses are probably more proximal than they are distal. So the center of gravity will be different depending on the torques that are produced by those individual segments. Why? Because each segment has the ability to move. As I mentioned earlier, moment arm is dependent on joint position. If moment arms are different, then therefore the torques are different. Okay, so in terms of center of gravity. So if we look at this here, this is the line that goes through the person's center of gravity that splits the left and right sides in the frontal plane, and in the sagittal plane that splits the front and back, or the anterior and posterior side, and in the transverse plane it'd be the top and bottom portions of the body. So that's the balancing point. That is the center of mass of the body, which is the intersection between the frontal, transverse, and sagittal plane. And as I mentioned earlier, in the vertical direction we call that the center of gravity. So as I mentioned, because torques will change depending on joint position, because of moment arms will change, center of gravity will also change. So just think about this individual, standing with his arms up in the air. If you were to raise your arms up in the air, you shift your center of gravity superiorly. If on the other hand you were to try to touch your toes, your center of gravity will also shift accordingly in the inferior direction. And so again, depending on body position and joint position will ultimately determine the location of that individual center of mass or center of gravity. And it's an imaginary point. It's not something that you can actually see. It largely depends, as I mentioned, on angular position. So they take, for example, this person performing a somersault. Because her trunk is flexed this way and her legs are extended and hips flex in this direction, her center of gravity is going to be off her body. It will be in front of her body, maybe closer to her navel area, right? Same with this person here. So I'm not going to go into details on how we calculate the center of gravity as a function of the torques. Just know that the center of gravity changes because of joint position that affects moment arm and subsequently affects the individual torques themselves. Now there's two points that I like to make about the center of mass / center of gravity. Any force that is exerting itself on the human body actually exerts it on the body's center of mass. And then in the vertical direction, it's the center of gravity. Remember, center of mass, center of gravity is actually the same thing. Only difference is that center of gravity is just only in the vertical direction. So your weight, or the line of force of gravity, gravitational pull, as well as the ground reaction force, vertical ground reaction force, acts on the body's center of gravity. So when I talk about jumping and doing a squat, and I'm determining or describing the forces and motion of that individual, of that jumper, I'm really talking about that person's center of gravity.